So today we're going to talk about refraction and dispersion. So when you think about a material that's optically transparent, so we would say it's clear, like glass. Light can pass through glass. But what happens when it's actually in the glass? And so if you think about a wave of light and it comes and it strikes an atom, it's absorbed by that atom. The electrons in that atom transition to a higher energy level. And then eventually that atom, the electron falls back to its original energy level, and that electromagnetic wave is transmitted on. And so it kind of, in a sort of crude model, it gets gulped up by one atom and burped onto the next, which then has electrons in a higher level, and then they kind of burp it on. And so the idea is that an electromagnetic wave, a ray of light, basically can pass through some materials if they have this property of being able to absorb that frequency and then retransmit it a little bit later because of their electron configurations. So this process allows light to pass through some materials that have the right frequency characteristics, but in doing so, the light slows down, sometimes significantly. So we call materials that allow light to pass through them optically transparent, but they always slow it down. So because it's always slowed down, the speed of light inside of these materials is slower. So we measure this effect with a parameter called n. And we call n the index of refraction, but it's basically just a measure of how much the light slows down. And so we define n as follows. N, the index of refraction, or you can think of it as a slowdown factor, is the ratio of the speed of light in a vacuum divided by the speed of light in a material. And since it always slows down in a material, V is always smaller than C, which means the ratio n is always bigger than 1. So n can never be smaller than 1. N equals 1 in a vacuum, and then it's always bigger for all other materials. So we're going to call it the index of refraction, which will make sense in a little bit. But you can think of it as a slowdown factor. So a quick little calculation here. In a piece of glass, light travels along at a slow 1.5 times 10 to the 8th meters per second. So in this case, what would be the value of n for the glass? So the value of n is the ratio of the speed of light in a vacuum, which is 3.0 times 10 to the 8th, divided by the speed of light in our glass. And so we have an index of refraction of 2 for this piece of glass, meaning the light slows down by a factor of 2 while it's in the glass. So here's some typical indices of refraction. For a vacuum, so that is basically empty space, it's exactly 1. And for air, it's very, very nearly 1. And the thing to note here that to 3 significant figures, it is 1. So unless you're operating in an environment where the tolerances are so tight and you know things so accurately, basically for air you can use 1 as the index of refraction. When light travels in ice, it slows down a little bit. It slows down a little bit more in water. In ethyl alcohol, it slows down. Glass is about 1.5 for most common glass, and for diamond it's a whopping 2.7. So what makes diamond special is the fact that light slows down so much because of the incredible density of atoms which are packed into the diamond structure. So now we get to the idea of refraction. So to help us understand what's going on, imagine a wagon wheel rolling along on a sidewalk. So it's rolling along at an angle here, and it hits a patch of grass. So because the grass causes the wagon wheel to slow down, I think you can probably tell that the wheel on this side right here slows down before the wheel on the other side because of the angle that it's coming in at. And that causes it to rotate a little bit and change directions as it goes from one media or one area to another where it changes speed. Now, you can imagine if this wagon wheel was coming straight down, both wheels would hit the grass at the same time and it would slow down, but it wouldn't change directions. But the bigger the angle of incidence, and we're going to measure the angle of incidence as the angle between the normal here and the direction it's traveling, so that's the angle of incidence. The bigger that angle of incidence is, the more it will bend, or the more it will change directions. We call this change in direction refraction, and it happens with light waves too. You've probably seen it. Here's some examples. If you have a straw in your Sprite, it looks like the straw is disconnected. The light from the straw is getting bent as it passes through the glass, and so your eye thinks it's coming from a different place. Here's another example. I've got a marker, and I'm looking at it through a lucite block, and so the light gets bent, and so the light that comes from the marker, which is really right here, is getting bent so that it looks like it's coming from over here. So we're going to draw some ray diagrams later that'll help us figure that out, but that's an example of refraction. So reflection is when light bounces. Refraction is when light passes from one medium to another and is bent in the process. So there's a little refraction simulator you can play with if you go to http://bit.ly/1229light. There's an app there you can play with, and you can change the angles of incidence and the angles of refraction, and you can see a simulation of how light gets bent. That's kind of fun and probably worth a couple minutes of your time. Okay, quick review of some Algebra 2, just in case you've forgotten. Sines, cosines, and tangents are functions that describe ratios of sides of triangles. Each is their own unique ratio of sides. And so you guys are probably all good at this, so I'm going to skip ahead here really fast. But really quick check on your calculator. Take the sine of 30 and make sure you're getting 0.5. If you're not getting 0.5, you're not in degrees mode. You've got to be in degrees mode to solve these problems. So the important thing here is that if you take the sine of an angle, you get a ratio. But what if you don't know the angle? You just know the ratio. How do you find this? How do you solve this problem? So if you know the sine of an angle is 0.8, you could start guessing angles and solve this by guess and check. And that's a fairly useful heuristic. But it's easier to use the inverse function. So just a quick reminder. The inverse function, if the sine of x is equal to n, so the sine of an angle is a ratio, then the inverse sine of the ratio will give you the angle. So we're going to need that when we solve some problems here. Sometimes we will know the sine of an angle is 0.626, and we want to know what is the angle. So on your calculator, if you hit shift before hitting sine, you'll get the inverse sine function. Sometimes it's denoted arc sine, sometimes sine with a little -1 here. And that's the inverse function. So we'll need that sometimes. You can practice it. If you take the inverse sine of 0.5, you should get 30 degrees. Because the sine of 30 is 0.5, so the inverse sine of 0.5 gives you 30. The inverse sine of the ratio, 0.5, gives you the angle. Okay, so here's how we're going to set up the problems. We are going to, anytime there's an interface between two optically transparent materials, so we're going to call one N1. So this characterizes the speed of light in the white area, N1, and N2 is the blue area. So imagine this is air up top and this is water down here, for example, and a beam of light is coming along. We are going to measure theta 1, the angle of incidence, the angle it comes in at. We're always going to measure that from the normal. So anytime there's a ray of light striking an interface, the normal is what we use to measure angles. So that's theta 1. And then here's theta 2. And then it takes a little bit of calculus to derive this equation, which is beyond the scope of this course. But it's not hard to show that the relationship between theta 1, theta 2, and N1 and N2 is given by what is called Snells Law. So this is the law we're going to use. The product of N1 times the sine of theta 1 is always equal to the product of N2 times the sine of theta 2. So when light is refracted, it follows this rule right here. So here's a table that shows you the indices of refraction for a whole bunch of different things. So when you're solving problems, you might need to use that. So here we're going to solve a problem. Light is traveling in air. So for air, index of refraction is 1. It strikes a body of water. So we're going to find water. Water at 20 degrees Celsius, the index of refraction is 1.333. And we want to know if the angle of incidence is 30 degrees, at what angle is the beam of light refracted in the water? So to solve this problem, we're going to start with a diagram. So there's our little diagram. We're going to make a list of variables. N1 is 1. Theta 1 is 30 degrees as measured from the normal. N2 is 1.33, and we got to find theta 2. So to do that, we are going to apply Snell's Law. We're going to start with N1 sine of theta 1 equals N2 sine of theta 2. And we're going to solve for theta 2. We're trying to find what's in here. So first of all, I'm going to get sine of theta 2 by itself by dividing both sides by N2. So if the sine of theta 2 is equal to this ratio, then the arc sine of this ratio will give me theta 2. So theta 2 is going to equal the arc sine or the inverse sine of this ratio. And you can then plug in the numbers. make sure you're in degrees mode on your calculator, and you can arrive at the conclusion that theta 2, the angle of refraction, is 22 degrees. And that sort of makes sense. If this angle was 30 degrees, and you imagine this is a wagon wheel, it slows down when it hits the the water, and so it bends towards the normal. This angle here is smaller than the incident angle, which is what we got. So that makes conceptual sense. Okay, so a quick note about which way it bends. If a ray of light passes into a more optically dense material that has a bigger n, then it bends towards the normal. Okay, so that's what we just did right here. When it passes into a more optically dense, n is higher, it bends towards the normal. So it would have kept going in this direction if there was no interface, but it bends towards the normal because it passed into a more optically dense material. And if it passes the other way, if it goes from a more optically dense to a less optically dense, it bends away from the normal. Okay, so at this point, it's probably a good idea to stop and solve some of the homework problems, and then come back here and restart if you want, or you could just kind of go on and get the rest of the ideas. It turns out that this index of refraction is very slightly different for different colors, because each color has its own frequency, and how long the electron stays in its state depends on the frequency and the energy of it. And so what that means is that, for example, in glass, the index of refraction for purple light is about 1.53, and for red light it's about 1.51. So this little chart shows you how the index of refraction depends on the color. What that means is that the amount of bending that will occur for violet light is slightly more than the amount of bending that will occur for red light. So, for example, if a ray of light comes and it passes through a prism, violet light gets bent a little more than red light does. Now, this is definitely exaggerated, but it shows you what we call dispersion. So dispersion is the spreading out of the colors due to the slightly different indices of refraction for the different colors. And so you guys would probably call this a rainbow, but we call it dispersion. And the angle of dispersion is the angle between the red and the violet light. So if you wanted to figure out what is the angle of dispersion, you could find the angle of refraction for the red light, the angle of refraction for the violet light, and find the difference. So that just means that each color reflects a little bit of a different angle, and it produces the color spectrum that we know as the rainbow. So dispersion is what happens that causes the rainbow. So what happens inside of a spherical drop of water is that light comes, white light comes, it starts to split up, it's reflected, or part of it is reflected off the inside edge of the water here, molecule, and then it goes here, and then it continues to get bent, and all of these processes cause the light rays to spread out, so they cause dispersion. So there's an example from a picture I took on vacation in Glacier National Park of dispersion, and it's actually a double rainbow over Glacier National Park. So what's happening is you've got all these raindrops in the air. The raindrops that are up here bend the red light to your eye. They also bend violet light, but that goes over your head, so you don't see it. So at the top of the rainbow, in some water molecules up here, you see a faint red color. And then the ones that are a little bit lower, they bend the violet light a little bit more, and so you see violet lower in the rainbow. And because this is a spherical droplet of water, this happens in 3 dimensions, it produces a spherical or a circular rainbow. In order to see a rainbow, you have to have the sunlight behind you. The sunlight's got to pass over your head, pass through the water molecules, and you have to be looking away from the sun. So in Indiana, generally, we see this when the sun comes out after a rainstorm has passed in the late afternoon. The sun is to the west, we're looking to the east, and there's still water droplets as the storm moves from west to east that produce the rainbow. Okay, so another example, what happens if you have a beam of light underwater and it's heading towards the surface? It's going to hit the surface at an angle of 55 degrees. At what angle is the beam of light refracted in the air? So here we have a beam of light traveling in the water. It's 55 degrees, and it's going to pass this way, and we want to know what is theta 2. So you can use your numbers and go ahead and plug them in and see if you can find out what is happening in this case. See if you can find the angle of refraction. There's going to be a surprise when you do. And I'm going to stop here and let you find it, and then you can continue with the slides to see what happens. Okay, you probably didn't try it, but if you did, you realize there's no solution. There is no solution because this quantity right here is larger than 1, and you cannot take the arcsine of a quantity larger than 1. So it means there's no solution. What that means, though, is that the light cannot escape. So we call this total internal reflection. When the ray of light is going from a slow medium to a fast medium, there's a special angle called the critical angle, and at that angle, the light cannot get out. If it can't get out, it's internally reflected, and it's totally internally reflected because none of the light can get out. So some examples of this: if we send light down a pipe, a fiber optic pipe, for example, if this angle is, if the normal, so here's the normal right here, if this angle here is large enough that light cannot get out, it just keeps bouncing down the pipe the whole way. It never gets out. So what's wild is you can have a clear pipe and you can send light down it, but the light can't escape the edges. It can only escape when it gets to the end. And so we call this a light pipe or a fiber optic cable. A diamond is a extreme example of refraction. A diamond is a very sparkly, pretty thing, and it's also very expensive. So what happens with a diamond is that white light, for example, passes into the diamond and it's refracted. Because of the way it's cut, this angle down here is greater than the critical angle and the light cannot get out. So the light bounces again, hits here, it can't get out, so it comes out the top. A beam of light which comes a slightly different direction gets bounced over here. So the story is that all the light that comes in the top of the diamond gets piped around and comes out the top, and all the light that comes in the bottom of the diamond also comes out the top. So basically a diamond is a funnel that takes all the light that hits it from any side and sends it out the very top along the edges. Okay, and that's what makes a diamond so brilliant and sparkly. So when you look at a diamond, you see a couple of things. First of all, you probably see a couple of flashes of the different colors. That's due to the dispersion. And it seems especially brilliant. So a diamond is always set up on prongs so that light can get in underneath of it here. And that light that gets in underneath of it also comes out the top. So if you just had a mirrored surface, it'd be shiny because it'd reflect the light. But a diamond is even better than a mirrored surface. Not only does the light hitting the top come back at you, but any light that comes in the bottom comes back out at the top too. And that's what gives the diamond its characteristic brilliance. And this happens because it has such a high index of refraction. Okay, so we've covered refraction, the bending of light, we've solved some problems, and we talked about internal reflection, total internal reflection. You've got a bunch of problems to solve and homework too now.